Why is the normal force called normal? In many problems, we see one object coming into contact with another, and in nearly all cases, the upper object exerts pressure on the lower one due to its weight. The lower object bends and in response pushes back on the upper object with an elastic force. To be precise, the upper object also bends, so both objects exert elastic forces against each other. This is consistent with Newton's third law, which states that the forces involved must be of the same type. As we also know, these forces are equal in magnitude and opposite in direction. Why are all of these forces called normal? Note that in each case, there is a plane separating the two objects, and the forces acting are perpendicular to this plane. In mathematics, a vector that is perpendicular to a plane is called a vector normal to that plane, or simply a normal vector. When we call a force normal, we're simply emphasizing that it acts perpendicular to a specific plane that bounds the object. To finally demystify the concept of the normal force, we'll examine a problem where two normal forces act on a body at the same time. Suppose a disk of mass m rests on two planes inclined at angles A and B. Let's find the magnitudes of the normal forces acting on it. As usual, we begin by drawing all the forces acting on the disk. The disk is acted upon by the force of gravity equal to mg and by two elastic forces N1 and N2 from the two surfaces. As we know, these forces are called normal to emphasize that they act perpendicular to the planes separating the surfaces from the disk. Now, let's write Newton's second law in formal vector form. mg plus N1 plus N2 equals ma. Since the disk is at rest, we can immediately substitute 0 for ma. To move from the general formula to specific calculations, we set up the coordinate axis, draw the free body diagram, and then apply Newton's second law separately for each axis, using the components of the forces along those axes. The most convenient way to solve this problem is to choose the x-axis horizontally and the y-axis vertically. Let's find the components of force N1 along the x and y-axis. The projection of force N1 onto the x-axis is N1x equals N1 sine c. Its projection onto the y-axis is N1y equals N1 cosine c. Angles A and C are equal because the first side of angle A is perpendicular to the first side of angle C, and the second side of angle A is perpendicular to the second side of angle C. How can we quickly verify, especially under exam stress, that we've correctly identified equal angles? We need to make the situation visually obvious. Let's try reducing angle A almost to 0. The angle equal to it should also shrink to 0. This test gives us confidence that angle C equals angle A. For the second force N2, we obtain similarly. N2x equals N2 sine d, and N2y equals N2 cosine d, where angle D is equal to angle B. Of course, we can also repeat the visual check to confirm that angles B and D are equal by gradually reducing angle B to 0. The gravitational force mg acts along the y-axis, so the magnitude of its projection equals the magnitude of the vector itself. Now that we know the components of the forces along both axes, we can apply Newton's second law in scalar form to each axis separately. Along the x-axis, Newton's second law can be written as N1x minus N2x equals 0, or n1 sine A minus n2 sine B equals 0. In a scalar equation, a vector's component is assigned a positive value when it is directed along the axis, and a negative value when it opposes it. That is why n2x has a negative sign. Along the y-axis, Newton's second law can be written as n1y plus n2y minus mg equals 0, or n1 cosine A plus n2 cosine B minus mg equals 0. The negative sign before mg, of course, indicates that this force is directed opposite to the y-axis. Let's look at the equations. We have two unknowns, n1 and n2, so two equations are enough to find the solution. First, let's rewrite the equations in a more convenient form. Second, we solve for n1 in the first equation. n1 equals n2 sine B divided by sine A. Third, we substitute the expression for n1 into the second equation to find n2. Finally, we substitute n2 into the first equation to find n1. Since these formulas are not obvious, let's verify our solution. To do this, we should check whether the formulas produce the expected result in a case where the answer is clear. Test 1. Suppose the disk has no mass. In that case, it will not press on the surfaces, so both n1 and n2 should be 0. By substituting 0 for m in the formulas, we find that n1 equals 0 and n2 equals 0. Therefore, the formulas yield the correct result. Test 2. Angle A equals angle B. In this case, the problem is symmetrical, so n1 should equal n2. Let's compare the two answers we got. The denominators in both equations are the same. And if sine A equals sine B, then the numerators are the same too. So, n1 equals n2. Test 3. Angle A is 0. In this case, the disk simply rests on a horizontal surface. The force n2 must be 0. Otherwise, it would push the disk to the left and it wouldn't stay in place. The force n1 must balance mg. If A equals 0, then sine A equals 0 too, and cosine A equals 1. By substituting these values into the formulas, we get n1 equals mg and n2 equals 0. So, the formulas give the expected result. An unusual test case, where g equals 0, also produces the correct result. Both n1 and n2 are 0. So, we can see that we solved the problem correctly.